Welcome everyone. My name is Eric Normand, and today I'm going to talk about functional programming and how you can use it to improve testing, reuse, and maintenance in your existing code base, regardless of if you're using a functional programming language. This should apply no matter what. Okay, so today I hope you come away with a new perspective on programming that you can apply to your code, new skills for writing better software, and some curiosity to seek out more. I'd like to start with a little story. Back in 2013, I started a meetup all about functional programming with some friends here in town. And every month, the discussion would always go to one of these basic questions about functional programming. The big one was, what is functional programming? Because we'd have new people coming in all the time. They were curious. And so that was a big, like almost every time we talked about what is functional programming. They also had questions like, why should I care? Like, I already know how to program. How will this help me? Another question was, should I just rewrite everything in FP? Like, is this an all or nothing thing? Another question was, well, I already know JavaScript. Can I just do FP in JavaScript? Or for that matter, can I learn FP in JavaScript without having to learn a new language? And after these discussions, I felt like I had a pretty good grasp on at least what I thought was important to explain to people and to be able to teach what we did as functional programmers. I've been programming in functional languages for about 20 years now. It's not a very common thing, and so I needed a lot of explanation. And people would ask me, what should I read? What should I go do? And I could not recommend a book. So I had to write it myself. So Grokking Simplicity is my attempt to take this idea of functional programming that's been kind of stuck in academia, at least in terms of how it's discussed in books, and give it to people from a perspective of practical commercial software, not academia. And to do that, I had to come up with a perspective on it that would allow me to teach it because I can't teach the whole thing. So I eventually wound up looking at functional programming as a set of skills. If you look at this Venn diagram, on the left, we have this orange circle that is things non-functional programmers do. And then the circle on the right is the things functional programmers do. So these are different skill sets. There's a lot of overlap. A lot of the stuff that functional programmers do, you'll do, everyone will do. But then there's some difference. And that difference is what needs teaching. And so that's what I focused on in the book. These are the things that professional functional programmers do that other non-functional programmers don't do. And then I had to come up with a linear order and a kind of organization scheme for how this is going to work. So I've discovered that there's really two levels. These levels kind of correspond to your level as a programmer, but because the second level requires the first one in certain ways, and the first one is actually necessary for the paradigm. So we're going to start there. We're going to go over both of these two levels. There's two parts of the book that correspond to the two levels, and we're going to start with the first one. So part one is all about distinguishing actions, calculations, and data. To my mind, this is a fundamental difference in functional programming versus other ways of programming. Functional programmers distinguish these three categories. So we're going to go over what each of them is, and then the next bullet, we're going to look at how actions kind of spread through our code. And then lastly, we're going to do a refactoring to extract out a calculation from an action. So let's get started with distinguishing actions, calculations, and data. So we can imagine a code base, and we pluck some code out of that code base. And we'll see stuff like this. So the first thing is a little bit of JSON. It turns out to be a JSON object. Then there's this function called send email. There's a function called sum. There's save user DB, string length, get current time, and then this array of numbers. Now I've starred 3 of these functions because they're different from the others in that it matters very much how many times I call them or when I call them. So for instance, send email, if I call that 2 times, the email is going to get sent twice. And I don't want that to happen. So I put a star next to it just to indicate it's different. Whereas if I have sum, I can sum the numbers as many times as I want. It's not going to affect the outside world, right? So you can imagine how send email would be harder to test because you might want to run send email 20 times to run 20 different tests. And now you have to deal with, am I actually sending these emails? Likewise, save user DB. It depends. If you call it 0 times, it's very different from calling it 1 time. And then get current time. Every time you call it, it's going to give you a different time. So this is these all get a star. They depend on when they are run or how many times they're run. So functional programmers will put all those starred functions above the line, and we'll call those actions. Okay, that's the term I came up with that I'm using in these slides and in my book. We'll talk about what functional programmers generally call these later, but we'll call them actions for now. So now there's everything else under the line, and there's a difference between just bits of data and a function that you can run. So we'll draw another line. Below the line will be data, and then above that line between actions and data is calculations. So calculations are actually things that you can run. They're functions or operations, operators like addition or multiplication that don't have an effect on the outside world. They're just computations. And then the data are inert things. So let's go over each one and give precise definitions. Actions, if you look it up in the dictionary, one definition you might find is the process of doing something typically to achieve an aim. And I think that captures what actions are all about. They're trying to do something external. It's not just thinking about it, it's actually doing the thing. We call them in FP jargon, you might have heard these terms before, impure functions, effects, or side effects. So these are the terms that you'll hear outside of these slides in my book. I use the term actions because I think that these are misleading and confusing when you're a beginner. So for instance, function is both a mathematical concept and a language feature, and they're different. And then effect, it's not a great term because it's actually, we're talking about the cause. So the cause of the email being sent is the function that's called send email. The effect is the actual email that arrives in your inbox, right? So it's not quite the effect, it's the cause, but then cause isn't the right word either. I had to come up with my own term. Okay, and then there is a rule of thumb for identifying them. Actions depend on when you run them or how many times you run them. When you run them, that's like the order that you run the actions in. And then how many times you run them, that's repetition. So if you call it 0 times, 1 time, 2 times, what happens there. Next, we have calculations. Dictionary definition is computation from inputs to outputs. In FP jargon, we're going to call them pure functions or referentially transparent functions. Again, it's problematic because in a lot of languages, they are not implemented as functions. I mentioned before the addition operator, plus, times, divide. Those are calculations. They're pure. They don't have any side effects. They're not actions, but they're not functions either. So I came up with this term, calculations. and they are eternal, outside of time. I mean, imagine addition. It's never going to change. Any machine you run addition on, it's going to give you the same answer forever. You know, you can't imagine it changing. If it does change, we'll be in big trouble. Okay, data, facts about events used as a basis for reasoning, discussion, or calculation. Data is kind of the most boring of them because they're inert, but I think they're actually quite interesting in themselves. They're serializable, they're self-identical, meaning they are what they are, which is kind of interesting. You know, a function is kind of opaque. You don't know what it's going to do really until you call it. Whereas data, you can read it. But the downside of data is that they require interpretation. So you need software to parse it and make assumptions about what it means in order to use the data. So we're going to talk mostly about actions and calculations because data is not, there's not as much to say. The big distinction is when you're writing code. So the thing is, functional programmers tried to write way more calculations than actions. Like more code should be in your calculations than actions. Basically as much as possible in calculations, actions only when necessary. Why? Because actions depend on time and it's just a pain to work with. They're much harder to deal with, as we'll see. The thing is, though, that we pay much more attention to actions. We spend more time with actions because they are harder to work with. And this is kind of a common misconception in functional programming, that we don't want to use actions at all, or that you know, we basically try to ignore them. We actually spend a lot more time and a lot more attention making sure that our actions run correctly. And I think we spend it more than other paradigms. So it's kind of interesting that there's that kind of duality. We spend more code on calculations, but then more attention on actions to make sure they're right. All right, we're going to talk about the spreading rule. Let's imagine this programmer has some code and she can correctly identify that this function called send payout is an action. We should go through what the code does. So down at the bottom, there's the main function and it calls affiliate payout with the affiliates. Affiliate payout is going to loop through all the affiliates and then call figure payout for each one. And figure payout is going to multiply the sales from the affiliate times the commission. And if they're owed more than $100, it's going to send the payout, meaning it's going to contact the bank and transfer money to their account. Obviously, send payout is an action. It's physically, or you know, it's reaching out to another system and sending money to them. So if you call it twice, it's a big deal. You're giving too much money. But is the rest of her code actions? She claims it's only got this one. So let's apply the spreading rule and we'll learn it as we go. So we'll start with that one highlighted action. Now, one rule of the spreading rule, or one part of the spreading rule, is that a function that calls an action must itself be an action. Because now if I call figure payout twice, well, that's going to send the payouts twice too. So figure payout also is an action. And because that's an action, we have to highlight the place where it is called in the next function. But again, we can continue, you know, recursively applying this rule. Oh, sorry, you can't read that down there. We can continue recursively calling this rule. And of course, affiliate payout is an action because it called the action. And so now we have to highlight affiliate payout in main. And then, all right, now main is an action and nothing calls main, so we're done. But the thing is, it's all actions. You have actions at the bottom of your call stack, you know, the top of your call stack. Everything under that, all the way to main, is going to be actions. And so this is one of the problems that functional programmers have recognized in using actions in like anywhere in the code, is that they spread. They just spread all up until main. So you're going to have actions in your code. We need to send that email. Like that's what the software is supposed to do. We need to send payouts, but we just have to identify and be conscious and mindful of what is an action. So this spreading rule helps us see that, yes, if you put action somewhere in there, it could spread all the way and infect everything. We'll talk about the problems with actions in a moment. First, let's talk about extracting calculations. So this is a refactoring that will let us take some existing code that's a mixture of actions and calculations. Maybe it's one big action, and extract out a piece of it that could be a calculation. So here's a function called showTotal. It initializes total to 0. Then it loops through the items in a for loop, right? Items is some global variable somewhere. And it's going to add the price of each item to the total. And then at the end, it's going to set the inner HTML property of this DOM element to total. So it will show it in the web page. We can deduce a couple things. The first is that the red elements are actions. So let's start with items. So we're reading the value of a global variable. And a global variable could change at any time, right? Calling showTotal when the items has 20 things in it is going to be different from calling it when items has 10 things in it, right? So now showTotal depends on when it is called because it is reading items. Likewise, it is setting something in the DOM. So if we call it again, I mean, maybe this wouldn't change the DOM because you'll get the same total calling it 2 times. But if we called it 0 times versus calling it 1 time, that would definitely be a difference. So that part is an action. But I've highlighted in blue all of this other stuff that's not really an action in here. This iteration through the items array and updating total, adding to total, like all that stuff it's going to give you the same answer. If items were the same, this total is always going to be the same. So we can probably look at this blue stuff and try to extract that out as a calculation. We do that, we make a function called sumTotal, and it takes items as an argument. And then we have this for loop in there. Now items in here is blue because it's the argument. Once it's passed in, it's not going to change. Because, we can, if we need to sum a different array, we can just pass it in. We don't have to assign it to a global variable. And then it's going to return the total at the end. And now showTotal, instead of having the for loop in line in there, it's going to call sumTotal. And I made a mistake. Items should be red because it is still reading from the global variable. So this items thing should be red. And then, of course, this is unchanged. So notice we've built a calculation called sumTotal. We've moved a lot of code out of this action and into a calculation. Now let's go a little bit deeper in what we actually did here. These 2 reads to items, these are actually implicit inputs to our function. They're implicit. The explicit inputs to a function are the arguments, but these are implicit inputs. It's data entering the function that doesn't go through the arguments. And then we are setting the inner HTML property, modifying the DOM. That's an implicit output. The explicit output would be a return value from the function. So we have an implicit input and an implicit output, and we've replaced them with explicit inputs and explicit outputs, at least in our calculation, right? So this is the refactoring that we're trying to do. We're trying to identify how does data enter into the function, how does it leave, and only use arguments and return values to do that. And we could just write it out like this: replace implicit inputs with arguments and replace implicit outputs with return values.